So there is one last concept of descriptive statistics that we need to know in order to better understand, in fact, to understand inferential statistics. Before, I'd like, again, to just review and have as clear as possible the concept of a normal distribution, of how the data is distributed in a normal curve. We spoke about in the last screencast about how normal human characteristics, or common human characteristics, I should say, are distributed in a normal curve. Weight is distributed in a normal curve. Height is distributed in a normal curve or in a bell-shaped curve. Reaction time. In fact, it is argued that basically many or most types of measures, or most measures, if you collect a sufficient or a very vast, very large data set, it will all end up being reflecting a normal curve, because, and it makes sense, as we said in the past screencast, that normally people will fall in the middle, right? So hopefully that is understood. And then another thing I wanted to mention that I forgot to mention in the previous screencast is that a good way of looking at normal distribution is also as a frequency chart, or a frequency distribution in a way. And if you saw that, for instance, in which each score is we go through this line, right? And picture this line as being the height of the line from the x-axis is the number of people that scored that. So, for instance, whoever scored whatever is marked here, that would be 1, 2, 3. Like, the height depends on the number of people. So this could be like 1, 2, 3 people scored whatever this score represents, right? And then this, whatever this score represents here, we could count 1, 2, 3, 4, 5, 6, 7, 8. So, as I don't know if that helps to sort of clarify how scores are distributed. You can see the height of this curve as people mounting up on each other, and that the higher, of course, the taller this mounting of people is, the more people scored that particular score. So, again, normal distributions, they basically explain that most of us will fall within the middle of whether it is demographic characteristics or standard scores on standardized testing. I also wanted to repeat and emphasize a bit is that the important thing about normal distributions, the relevance it has in psychology research, is that it provides us with information already, without doing much with it. And I explained, and this is something you need to know, is that, and here it's sort of better formatted, that, we have the mean, correct? The mean is, and the median and the mode, but the mean of in this case, it's Wechsler intelligence exam, IQ exam, measures IQ, and the mean of, as with most IQ tests, the mean is 100. So the standard deviation in this case, so if the mean is 100, and here we have a score of 115, and here we have a score of 85, you can already assume that the standard deviation is of how many points? Correct, 15. I feel like one of those cartoons that answers to the audience with these answers feels a little ridiculous, so I apologize. So, so the standard deviation for the Wechsler intelligence score test is, standard deviation is 15. So we can already know, if we have the standard deviation, if we have the mean, we already know how many people scored from the population, how many people score within one standard deviation above and one standard deviation below. Here we know that 68% would score between 85 and 115, and so forth, as we explained in the previous screencast. And I think I also forgot to mention, just to make it clear, is that in any normal distribution, can't erase on this, but okay. So in any normal distribution, one thing to have very clear, and then maybe by dividing it, in halves, you can take it from there. But there is a good part of normal distribution, or the information it provides us with, is that we already know that 68% will score. 68% will score within one standard deviation away from the mean. So we know that 68% of people scored between 85 and 115. That I already explained. Okay, so then the next number would be 95, as it says here, but we're going to put it with a different color. So 95% of people will score within 2 standard deviations above or below the mean. So what is in red is 95, and then the third standard deviation, which is as far as normally it goes, because it includes almost everybody in the population. So that would be 97%, 97.7, I believe. Yeah, 97.7 would score within 3 standard deviations. Okay, so that's a good way also to remember. I'm pretty sure it's also called the empirical rule. Those of you taking AP Stats could please verify that, if you may, in class, please. So this just short review is a way to reiterate the importance of normal distributions and the amount of information it can provide us if we have certain pieces of data, such as the mean and standard deviation for a particular test, or for height, or for weight. We can automatically know a lot from a set of data. So what are z-scores? Z-scores are basically, z-scores, what they basically do is tell us the number of standard deviations a particular raw score is from the mean. So if you have, if you scored, let's say, in this, I believe this is also an IQ test. We have the standardized scores here, and this is, I would put the raw score for the IQ. Let's put it that way, so I don't want you to get confused with the standardized. So IQ scores, let's say somebody who scored 115 on this IQ test, right? That means, it says right here, it's 1 standard deviation above the mean. This means that this person that scored 115 their z-score is +1. And by knowing that someone's z-score is +1, remember, we can also we can get a bunch of data, like the percentile. What is their percentile on this score? So 115 z-score is +1. The standard deviation seems to be 15, like in the previous test. So so this means that 34 plus 34, 68. 68 plus 14, that would be 12, 82. 82 plus 4, 82 plus 2, sorry, that would be 84. So this person approximately would be in the 84th percentile. His or her z-score is +1. The raw score would be 115. And this is a set of scores. Since it's a standardized IQ test, we know that it has a normal distribution, so we can assume that the standard deviation is 15, and therefore this is a score that can be compared with others. So again, a z-score is basically a score that is going to tell us the number of standard deviations a particular raw score is in relation to the mean of the normal curve. But then, what are z-scores good for? If we already have the standard deviation, what are they good for? Well, z-scores are good to compare scores from different, completely different scales. You know how they normally tell us that, to tell us that we're comparing something that can't be compared, they tell you, well, that's like comparing apples to oranges, or perhaps, your parents say that a lot. Well, actually, z-scores do allow us to compare apples with oranges, and I'll explain this in a minute. When we're trying to measure two different values from two different scales, z-scores will help us because they're basically taking both of these scales and both of these scores to a common ground. I think this example will make it clear for you. So I have two friends here, right? I have Amy and I have Tim. And Amy and Tim have this ongoing competition as to who is more accomplished, who is smarter, and they have this very, sort of pathetic competition going on. And Amy took the ACTs, and Tim took the SATs. And they keep saying that one is better, that, Tim says that he is smarter than Amy and vice versa, and that he got this score in the SATs, and so they have this competition going on, right? So, but how will we know? Well, we have two different scales. We have two different tests, right? And the scores, the range of the scores from the SATs are very different from the ACTs. But if we have information from these measures, right, because both of them, okay, please excuse my horrendous bell curves, but if we have some information from each of these, then we can compare Tim's SAT score and Amy's SAT score. For instance, I think Amy, how much did Amy score? She scored a 31 on her, that's her raw score from the ACTs. And Tim scored in his SAT, scored a 625. So if we have if we have more information, then we'll be able to compare both Amy's and Tim's score and say who scored better, and then solve all the problems of the world. So, actually, the formula for z-scores, well, before we go into that, another piece of information that we need is the mean for each of these tests. So, based on the data I found on the internet, the mean for the I always mess up that. ACTs is a 21. That would be sort of dividing the bell curve for the ACTs in half, right? And that would be the 50th percentile. And the the mean for the SATs is 500. And again, what we're trying to do here is with z-scores, I'm trying to show you how z-scores can make two raw scores from two distributions in comparable. And then finally, the third piece of information that we need is the standard deviation. And usually with standardized tests, especially for a particular year, that information is readily available. So based on what I found, the standard deviation then, so the SATs, Amy scored a 31, that's a raw score. Tim scored a 625. SATs, the mean is 500. For ACTs, the mean is 21. I should notate that. So the mean x bar, the mean for the ACTs is 21, and the mean for the SATs is 500. X bar equals 500. Okay, so now we're missing the standard deviation, which I found, and for ACTs, the test for the ACTs, it's 4.7 is the standard deviation, and for SATs, the standard deviation equals 100. So now with this piece of information, we can calculate the z-score for Amy, a z-score for Tim, and see who scored better, and to end this very life-shattering competition between them. So basically, what you have to do is plug in that information that I provided you in the previous slide, saying that z-score equals the score, right? If you subtract the mean of that particular population that we're using from the individual score, right? X is the raw score, and you divide it by the standard deviation, you will have a z-score. So let's try to do that with Amy's information and with Tim's. So the z-score for Amy, if she scored on her ACTs, right? She scored 31, and the mean is 21. That would be 10 divided by the standard deviation, which is 4.7. And yes, I already calculated this before preparing the screencast this time, and that takes us to a z-score for Amy equals what is it? Where is it? Oh, something 2.1. 2.1. So basically, Amy z-score by being plus 2.1 or positive 2.1, that means that Amy scored a little above 2 standard deviations above the mean, because it was exactly 2.1 standard deviations above the mean. Now Tim scored 625, right? That's his raw score. We're plugging in the information from here for those who are just joining us right now. And then we subtract the SAT's mean, which is 500. And then we divide that by the standard deviation. And standard deviation for the SATs is 100. And that leaves us with 125 divided by 100. And that would give Tim a z-score of 1.25. So now that we've converted their raw scores from two different scales into z-score, it's sort of bringing, how can I put this? It's like z-scores are basically a bell curve of standard deviations in a way. It brings two different scales into common grounds, and then by calculating based on the standard deviations, z-scores it gives us a value that make these two different scales comparable. Now, Amy, by scoring 2.1, having a z-score of 2.1, that means that her score is significantly better than Tim's. And then you have to be very aware of what this means in relation to what z-scores mean in a normal distribution, right? So here I tried to find, I would like you to forget about these t-scores. I'll leave that for the AP Stats people. Here what is important to us is the z-scores, the cumulative percentage, which are the percentiles, and we have the standard deviations from the mean. I would say this, let's forget that. Okay, so here on this scale, basically, it's someone who has a z-score of 1 would be here. Someone with a z-score of 2 would be here. Now, what you have to be aware of and start thinking about is that if you know the empirical view and you know what percentage of people fall within standard deviations of a normal curve, if on a test someone were to ask you, well, I don't know, what do we say, Amy scored 2, let's say 2, her z-score equals plus 2. Let's say her z-score was 2 plus 2, then how many people scored how many people scored above or how many people scored below Amy? So, well, you know, because you understand this very well, that z-score means that this person scored 2 standard deviation above the mean. If you know already that this makes sense, that all this is 50%, right, of people that took this test, right? And you know that this right here is, and here we have the 34, right? So that would be 84 plus here for between 1 standard deviation and 2 standard deviations, that would be approximately, I think it's 13.5%. So then we add this up, 50 plus 34 is 84. 84 plus 84 plus, so that would be, so Amy scored over close to 97%, above or equal to 97% of people in the ACTs. So yeah, so now Amy can really tell Tim that she won this competition, and that's it for Z-score. So again, try to just consider that Z-scores are a way to are standardized scores that, based on standard deviations, can make two scores from different scales comparable on a common ground, on a common normal curve. Thank you.